the concept we want to get is of open loop and closed loop. In simple words, open loop means a system without feedback, and in closed loop, we have the system's feedback. As an example of closed loop, let's say we want to control the speed of pump using the pressure feedback or the flow feedback, or we want to control the motor RPM based on shaft's feedback, or based on temperature feedback we want to regulate the fan speed. So we see on the screen a simple image. There is an input which is our set point or the target, and the controller does some calculation and gives the output. Along with that, it is also receiving feedback to improve its calculation, which is intended to produce the output which is near to the target. So let's take an example. We have pump controlled by VFD and the control is based on pressure feedback. So let's say if the pressure is getting lower than the target, then the VFD will increase the speed of pump so that it reach near to the target. Based on this information, we are ready to discuss PID. We will understand PID using the example of pump with pressure sensor. We have case 1. When the feedback indicates low pressure, then the action will be increase the speed swiftly. Case 2 will be when there is less difference between the set point and the feedback. However, still the feedback is indicating it didn't reach the target and it is still lower than the target. So the action will be increase the speed, but this time it will be gradually. In case 3, when the feedback and the set point are equal or they met, then the action of VFD will be to keep the same speed so that the system maintains the same level. And in case the feedback exceeds the set point, then the action will be reduction of speed. If feedback exceeds slightly, the reduction of speed will be gradual, and if the feedback is far away from the set point, then the reduction of the speed will be faster. So with this example, we get some idea about how PID works. However, before we move further, we need to know why PID. What other options are used? To answer that, we again take the same example. So let's say this pump system is for domestic water supply and the requirement is to keep 4 bars and the minimum acceptable pressure is 2.5 bars. So the controller I will use will give output when the pressure gets below 2.5 bar and will supply until 4 bars and then stop. Then it will restart again if the pressure goes below 2.5 bars. Now in theory it might seem acceptable, but practically the system is quite annoying. The problem could be pressure overshooting, since at 4 bar it will cut the supply, but since there is a momentum in the system, the pressure will overshoot. Second problem could be low pressure. So in the system which we discussed, it is supposed to start at 2.5 bars. But during the water usage, this pressure difference will be visible. And the third problem we have is surge in water pipeline. Since without PID, the operation is simply pump on and off without the use of VFD. So that means when the pump is starting, it is starting at its full speed and it can create a water surge. So we can say that overall system is not smooth. Now imagine if instead of system continuously switching to on or off, we can maintain a constant pressure which is 4 bar all the time. That's where PID has to offer. Based on this information, we can summarize that the job of PID is getting to the target by taking feedback and to remain on the target. Now we can get more into this topic. PID has 3 components. P stands for proportional, I stands for integral, and D stands for derivative. Talking about P, which is proportional, as we can see in the image, there is target and feedback which then subtracts and the result is then multiplied with the Kp value, then we get the gain value. Next is I integral. In P, which is proportional, we get information about the difference or error value, which we can visualize by an example. If our set point is 4 bar and feedback is 3 bars, so the difference is 1 bar. To improve the output, VFD will raise the motor speed. But here one component is missing, which is how fast or how slow should I increase the RPM. That's the job of integral. We can see in the graph how P and I will respond. It is responding as we discussed in the cases before, but note one thing. Here we see there is some oscillations. Sometimes it doesn't appear, but it can happen. So how about if we reduce this oscillation here at this point, but for that our controller should be capable of prediction, which tells in advance that this oscillation might happen and I should recalibrate my output so that this oscillation could be avoided. And that's the job of derivative, the last component of PID. So comparatively, this is how the graph will look like. In next video, we will do practical to get some idea about PID working.